You've been testing a standard password reset flow in ASP.NET Core for hours, but the system keeps pushing back. This developer's post shows the exact failure point. Inside the reset password async block, the method returns an invalid token error. The server generated this token moments ago. The user never touched it, yet it's rejected the moment it returns. In a typical workflow, the backend creates the token, sends it as a link in an email, and the user's browser sends that link back to the API to complete the action. Cryptography is built on exact matches. If the cryptographic string isn't manually altered by an attacker, the system should recognize it as valid. This specific error indicates a cryptographic signature failure, which persists even when your application logic is perfectly sound. The invalid token response occurs because of a silent deformation of the signature that happens while the data is moving through the network transport layer. ASP.NET Core Identity protects account-level operations by generating opaque tokens using standard base64 serialization. A standard base64 string relies on specific characters, like the plus sign, that are incompatible with how URLs are parsed. The backend embeds this string into a query parameter. This is the point of failure. Browsers automatically interpret the plus sign in URL as a blank space. This modified string, now containing a space where the plus sign used to be, is sent back to the API for processing. The backend API reads the variable exactly as the frontend transmitted it, unaware that the string was altered while it was in transit. The frontend router's automatic URL decoding functions as an unintentional data corrupter, permanently altering the cryptographic payload and breaking the signature. When that modified token returns, the ASP.NET Core Data Protection API acts as the gatekeeper, verifying the payload before it reaches your application code. The hash function processes the intact token to create a specific cryptographic fingerprint. When we feed the algorithm the corrupted string containing a blank space, it outputs a completely different fingerprint. Because the fingerprints don't match, the security check is triggered and the token is rejected. A common mistake is attempting to fix this on the backend by wrapping the incoming variable in a URI.unescape data string call. Unescaping fails because the plus sign is already replaced by a space. There is no original character left to unescape. Since even a single altered character changes the payload's hash, the framework rejects the token to prevent a potential tampering attack. Fixing this requires a change to your encoding strategy. ASP.NET Core includes a specific utility designed to prevent this transport corruption, webencoders.base64 URL encode. Before the token leaves the server, the encoder converts the unsafe plus character to a hyphen and the / to an underscore. It also removes the trailing equal signs used for padding, resulting in a string that can move through a URL safely. To process the token, you must use the inverse method, base64 URL decode, to restore the original base64 string before it is hashed. If we look back at the developer's original notes, this architectural fix was actually present in the commented out code the entire time. Using these two methods together ensures the token survives the front-end routing process without a single character being changed. Ensuring tokens survive the trip through a URL fixes the corruption issue for opaque identity tokens, but it also highlights a separate challenge: the lack of visibility into why other security tokens, like JWTs, fail in the same pipeline. We need to look beyond account-level tokens to the primary method for API authorization, JSON Web Tokens, or JWTs. Unlike the opaque binaries used by identity, JWTs are structured JSON payloads that use base64 URL encoding to store readable claims. When a JWT fails a signature check or an expiration validation, the ASP.NET middleware follows a secure default and returns a generic 401 unauthorized response. Hiding the specific reason for the rejection is a security measure. It prevents an attacker from learning how the validation logic responds to their attempts. However, this leaves developers guessing. You might have a valid-looking token, but you have no server-side feedback telling you why the middleware is rejecting it. To debug these issues, you must explicitly configure the middleware to surface the internal framework exceptions during development. Treating security tokens as impenetrable black boxes makes debugging nearly impossible. Resolving authorization errors requires seeing exactly where the cryptographic validation is failing. This snippet shows how to gain that visibility. Within your Add JWT Bearer setup, You can enable the Include Error Details flag specifically for development. This flag instructs the server to append the internal error description to the www authenticate response header, identifying the exact cause of the failure. For a secure way to monitor these failures in production, you can hook into the JWT bearer events pipeline. By utilizing the onAuthentication failed event, you can intercept the rejection before the server sends the final response. As the log appears, this allows you to capture specific exceptions, like signature mismatches or expiration errors, and log them safely on the server without exposing those details to the client. For identity workflows, always use base64 URL encoding to prevent URL tarsim from changing your payload. For API authorization, always use middleware events to ensure you have visibility into why a token is being rejected. By utilizing URL-safe encoding and configuring middleware to surface diagnostic data, you replace guesswork with a clear path to resolving token failures in distributed systems.